Hi, everyone. This is Wei from the University of Queensland, Australia. And today I will give our presentation, Federated Unlearning for on-device recommendation. Our presentation includes 4 aspects. Background. In background, we will introduce some preliminaries and related works and motivations of our work. And then we will give a brief description of our methods. And finally, we will give our experimental results and conclusions. So let's first move into the background. So what's recommender systems? Recommender systems suggest the most appropriate items and services to users by analyzing the collected personal data. For example, user item interactions and user profiles. So here, I want to point out one keyword, collected. Collected means that a user should share data with the service provider. However, with some recent released data privacy protection regulations, doing such things may be becoming harder in the future. So researchers pay attention to another recommender systems named the Federated Recommender Systems, FedRACs. FedRACs can train recommender models on each user's client's devices, so we do not need to share data with the central server, which seems to be more privacy preserving. And since the first federated recommender systems were proposed, many extension versions has been released in recent years. However, most of these works are focusing on how to efficiently and effectively learning user data. None of them focus on how to forget specific users' data during training process. We argue that without the forgetting ability, FedRACs still take risks of breaking privacy protection regulations because all of these regulations explicitly claims that a user have the right to be forgotten at any time. And besides, with the forgetting ability, we can improve the FedRACs security level because current works already point out that FedRACs are vulnerable to malicious users. And if we can erase the malicious users' influence during training time, we can let our FedRACs be more safer. Of course, some machine learning works has been proposed from last year in recommender systems. However, all of these works are focusing on centralized recommender systems, and their learning methods are generally based on SRSA, which require to access the whole dataset of the recommender systems. But this is not allowed in FedRACs, so their work cannot be applied in FedRACs. Besides, some learning methods are employed in the federated learning. We call them federated unlearning methods. But these methods are applied in the classification tasks, and compared to classification tasks, FedRACs has some differences. For example, in FedRACs, we have a large number of clients. So if we want to apply this Fed unlearning methods in FedRACs, we should do some modification. And in this paper, we explore unlearning in FedRACs. Generally, we choose one federated unlearning method named Fed Eraser. The idea of Fed Eraser is to keep all items historical updates. And then when we want to, when some clients want to quit, we just need to modify the stored historic updates and roll back the system to a new state. But and the theory in FedRACs, in this paper, in Fed Eraser, is that we only need to calibrate the historic updates direction because the direction get the model to fit on a data set. And when some clients ask to quit, the data set is changed, so we need to change the direction. But we still can reuse the historical updates length. So since we only need to search a new direction, compared to retraining the model from scratch, we can use fewer local epochs. So here lambda is a speed up factor, and in our experiment we showed that actually we only need to set lambda to 0.1. That means we can theoretically get 10 times faster than retraining from scratch. So after we search for the calibrated direction, we just need to aggregate this modified direction to get a new Federax. But as we mentioned in Federax, we have a large number of clients. So how to store these updates becomes a question. One simple way is to store them in a central server. However, the cost of storage will linearly increase with the client number. Another way is store them on device. But as we know that users' devices storage is limited, so we should find an efficient way to store the historical updates. So here we first analyze what the composition of the cost. It includes generally includes from two aspects: interacted items and negative samples. To reduce the whole cost, we propose an importance-based update selection method to select some important items to store. And to reduce the number of negative samples, we find a more efficient sampling methods to reduce the number of negative samples, but still achieve comparable performance. So for the importance-based update selection, we instead of storing all the embedding updates, we only store important updates according to their magnitudes. And in our experiments, we find that even we discard half of the updates, we can still achieve comparable performance. And for the sampling methods, this method contains two parts: user semi-hard negative sampling and item semi-hard negative sampling. For user semi-hard negative sampling, it's actually the same as in the traditional recommender systems. We use user embedding to search for the hard samples. But in Federax, only users were selected will have the chance to update their user embedding. So the user embedding will take a long time to be informative. So before they be informative, we use item semi-hard negative sampling method to search for the hard samples. That means we use the center of the user's interactive item embeddings as the fake user embedding to search for the hard sample method, hard samples. And here are the storage cost analysis, and you can find in our paper. And because of the time limit, I will not detailedly introduce this thing. And this is a pseudocode. Another challenge of federated unlearning in Federax is that how to evaluate them, because there are a large number of clients. So removing one normal users, it will be very subtle for their contribution, so it's hard to quantify their influence. So here we construct a group of malicious users, and these users aim to destroy the recommender Federax. So after they destroy the recommender systems, we apply our unlearning method to remove their malicious influence and to recover our Federax. And we use retrain as our baseline. So retrain means that we retrain the model on the remaining users without malicious users. So compared to retraining, we can see whether our method can remove or recover remove the bad influence and recover our system. So as we can see from this table, attacked means that the system has been destroyed. And the retrain is the system trained on the remaining users. And we can see our unlearning methods can recover the system and even achieve better performance than retraining method. And besides, retraining will cost lots of time. As we can see in the right figure, our methods is much faster than retraining methods. So it will efficiently reconstruct a new recommender systems. We also do some ablation study to show the importance of some hyperparameters. And So in conclusion, we take the first step to propose to apply Unlearning method in FedRACs and conduct experiments to show the efficiency and the effectiveness of our FedRACs Unlearning methods. So that's all. Thank you.